Hello, and in this example we're going to continue on with graphing more parametric curves. So again, we defined a parametric curve being a relation of two independent variables, and in the past we saw x and y being both a function of a independent variable t, and in the last example we said t was time. So let's go ahead and try another graphing example. So let's go ahead and try another graphing example. I hope that doesn't start flickering again. Let's say that we want to graph the parametric equations, graph parametric equations. Let's say we want to graph something easy. X equals to cosine of t and y equals to sine of t. So we also are going to restrict this. We're going to restrict this to a set of boundaries to be 0, which is going to be less than or equal to a value of t, and this will be less than or equal to, let's say, a value of 2 pi. So 0, which is less than or equal to t, which is less than or equal to a value of 2 pi. So I'm sure some of us now at this point are actually seeing a really interesting relationship, and if you covered this in maybe your pre-calculus class, you might have already seen this graphing relationship, but we don't actually have to do that t-chart as we saw before. So in the last video we did a t-chart, and it wasn't even a t-chart, it was just a chart where we had t and then we had x and then we had a value of y, and then we would have started off with 0, then maybe increased by a value of pi over 2, and then we would have gone up to pi, then 3 pi's over 2, and then 2 pi. And then we could have graphed it as such. But one way to graph parametric equations is to eliminate the parameter. So when you eliminate the parameter, in essence, you're converting it back to a x, y, or y as a function of x, or y as a relation of x. And we're going to see here this is not a function, this will be a relation, but we can eliminate the parameter. So we know the relationship that x squared plus y squared is equal to a value of 1. We know that x is equal to cosine of t, and we know y is equal to sine of t as defined. So this actually works out very nicely. That sine squared, this is cosine squared plus sine squared, and this is a value of t, plus sine squared of t is equal to 1. And this graph is contained in the unit circle. This graph is contained in the unit circle, x squared plus y squared is equal to 1. And geometrically, the parameter t can be interpreted as the angle. So if I were to actually graph this, so let's go ahead and graph this on a plane. So I'll start off here being 1, 0. This will be 0, 1. This will be -1, 0, and this value down here will be 0, -1. So I'll graph it in red. So we, in essence, have a circle. So I can try my best to draw a circle. Let me just do it here. So we would have a circle. Notice the way I'm drawing the circle. Parameters have to indicate direction versus our prior curve history, which do not have direction. They're just a set of points. So our parametric equation will actually have some arrows in here drawing and implying the direction the curve is traveling, or whatever point is on that curve traveling. So here, doop, doop, like such, we know the radius is equal to 1. This is the value of x, this is the value of y, and this value here, and I'll do this in gray, this parameter could be our angle t. So if that makes any sense to you, the parameter t can be related or interpreted as the angle between the radial line and the origin. So in essence, we have this relationship that x, y is equal to cosine of t, sine of t. And as t increases from 0 to 2 pi, the point traces in a counterclockwise direction. And that's how we indicated the point going in a counterclockwise direction. That's with these little arrows right here. So these arrows right here, that's how we're indicating the point is going in a counterclock direction. And if we wanted to obtain different portions of the circle, we could vary the parameters interval. So notice here the parameters interval was originally between 0 to 2 pi. Notice what would happen if we would to restrict this between 0 is less than or equal to t, which is less than or equal to pi. So if we were to restrict it to between 0 to pi, we would only get the top half of the circle. So we would just get the semicircle on top, and that would be a function. So there's lots of different ways that we can relate the parametric equations and their restrictions, their boundaries, and then how it goes. If there was no boundary, then this would just infinitely go around and circle, around and circle, around and circle infinitely. So I find that to be interesting as well. But it does have an implication when you all go into physics and maybe you start working with a particle or an electron or a proton that's moving around. Well, electrons move around more than protons do. Electrons move around actually in a huge capacity. But when we have electrons that are spinning around, we will note that if the electron spins in a clockwise direction, we could have a very different outcome in the relationship that it has. So how could we indicate a clockwise direction? And that's probably a question some of you are thinking, is that how do we be able to draw this, or how do we be able to write this such that we have a clockwise orientation? So originally we had the relationship x equals to cosine of t and y equals to sine of t. But if we wanted to have it go in a clockwise direction, then we could rewrite this. So we could write that x equals to cosine of t again, cosine of t, but here we would say y equals to negative sine of t. And this would still be restricted from 0 to 2 pi. And now we have the negation of sine, and that means that our circle would in fact be going would be going clockwise. So that is important for us. And why would we not have a negative cosine here? Is because remember, one of our interesting relationships of cosine is that since cosine is an even function, then cosine of negative t is still equal to cosine of t. However, sine of negative t, sine is one of those odd functions, is equal to the negation of sine of t. So we would be able then to graph this with an orientation that is clockwise by negating our parameter. So just as a quick summary of orientation exists in parametric curves. Orientation exists in parametric curves, and often we might call this you might see this the direction. You might see it called the direction, or it might be the direction of increasing parameter. So if you see any of those terms, any of these terms, whether it's the orientation, whether you see direction or direction of increasing parameter, we're thinking that we are working with a parametric curve. If you are not working with a parametric curve and you're just working with a curve, just a curve that is not a set of parametric equations, then we just have a set of points. We just have a set of points, and that's everything we've been doing with functional analysis, is that we just have a set of points. So it's important for us to distinguish between parametric curves and regular curves, because parametric curves have a indicated direction. So as some of you may have seen in the past video, when I graphed the relationship, I hope I still have it on here. Yeah, here we go. So as I graph this relationship, notice the graphing calculator, well, let me just change this to, I don't know, let's change this to 4 sine of t. This might change it up a little bit. Notice here that it's moving, and it's moving in the relationship of the orientation. So you can often, if you use the graphing calculator, see the way the curve is graphed, and that will give you the direction of its orientation. Some programs out there graph so fast that you can't see it. So when you get to those level of classes, there are different techniques you can use to indicate and determine the direction and the orientation of the parametric curve. However, at this stage, You can graph it using a chart, or you can graph it using your calculator, and the calculator, as it plots it, will indicate the direction.